Hello, it's Stat 135, Lecture 2. So last time we looked at the case where our population was consisting of zeros and ones. And in that case, we're sampling from a box with zeros and ones. This is called the dichotomous case. And our xi are Bernoulli p. So p is the probability of having a 1. So an estimator for p is just the sample mean. And we saw that the expectation of the sample mean is just p. This is to say that p hat is an unbiased estimator, and as well the variance of the sample mean is given by the formula here, which includes a correction factor. And there are two estimates for the standard error of p hat, a conservative and a bootstrap estimate that we talked about last time, because generally we don't know what p is. So today we're going to tie ourselves to the book, and we have section 7.33. We'll talk about confidence intervals. Confidence intervals for the population mean, and in the dichotomous case, we have, for example, we can talk about a 68 or a 95% confidence interval for the population parameter p, and that's given by the formulas here, but we'll discuss this below. As you can see, the formula for the confidence interval involves the standard error of p hat, which if we approximate that using a conservative or bootstrap method, we also get a conservative or bootstrap CI for p hat. So we're also going to, I think we should talk about a confidence interval for p, not for p hat, sorry. And we're also going to cover section 7.3.1, the expectation and variance of the sample mean. Actually, we'll just get started with that today. So section 7.3.3, the normal approximation to the sampling distribution of x bar. So we have an example where we have a population of 393 hospitals, where our box consists of the number of patients discharged from each hospital, and we're choosing a sample of size 50. The population mean and standard deviation is given, and we're taking an SRS of size 50. In other words, we're drawing without replacement. And so just a little bit of practice, finding probabilities. So we want to find the probability that we're in the tails. Now, x bar is approximately normal by the central limit theorem. So, and we know that it's centered at mu, which is 814.6. We just need to find the standard deviation, but we're given that by a formula from above for the distribution of x bar. So we need to find the shaded area, so we normalize, and once we get the standard normal curve, we can compute the CDF, and the 914.6 converts to 1.28, and so we just need 1 minus capital Phi 1.28, which you can find using the pnorm command in R. So then I asked you guys to do basically the same calculation for the dichotomous case, and there's absolutely nothing different here. So I won't say anything more about that. We then went on to confidence intervals. And confidence interval for a population parameter theta, it's a random interval calculated from the sample that contains theta with some specified probability. So if you specify some alpha between 0 and 1, z alpha is that number such that the area under the standard normal curve to the right of z alpha is alpha, that's shown in this picture. You can find z alpha using the q norm function in R, since z alpha is the 1 minus alpha percentile, meaning that it's that number such that only alpha percent of your data is larger than z alpha. And so the probability that that our standard normal curve is between minus z alpha over 2 and z alpha over 2 is 1 minus alpha, as you can see from this picture. So for example, if alpha is 0.05, you can show that z alpha over 2 is 1.96 using the q norm command. And so we just do some straightforward algebraic calculations here, manipulations, and we get the 1 minus alpha times 100% confidence interval for mu given by this formula here. So what is important is understanding what this means. So for example, if alpha is 0.05, there's a 95% chance that the random interval, the 95% confidence interval, contains mu. So make sure you understand that this interval here is random. Mu is a fixed constant. So the variability is with the interval. So we say that there's a 95% chance that interval contains mu, not that there's a 95% chance that mu is contained in the interval, because the probability you want to say that is a probability of the interval, not a probability of the constant, because the constant is either in the interval or not. Because it's a constant, there's no variability about it. But anyway, I'm talking too much. So here's a good illustration of this. So what we have here is we have a population containing 80% red marbles. You're taking out a sample and you're getting a confidence interval, 95% confidence interval for the percentage of reds in your population. And out of 100 confidence intervals, 95 of them contain the true population parameter. So I just gave like a simple example here of asking you to find a confidence interval and to interpret what it means. And finally, we started section 7.3, and so it's important you understand what an unbiased estimator is. So it means that the expectation of the estimator is the population parameter itself. And so so we show here that indeed the sample mean is an unbiased estimator for the population parameter P in the dichotomous case. And I just gave you a quick exercise doing some calculations here that involved you realizing that you can write the variance of y as in terms of expectations as shown here. And this was an intermediate step to actually showing that the sample variance given by the formula here is an unbiased estimator for the population variance. and its proof is here. And I asked you guys to study this. We proved together up to the second box, and I ask you to go and just verify all the steps to the bottom. I'll see you next time. Have a great weekend.